Hi, this is Matt McCormick. I'm in the philosophy department at the California State University, Sacramento. My email address is mccormick@csus.edu. And this is my second lecture for my inductive logic class, Phil 61. My second lecture on an introduction to Bayes' theorem. This is part 2. All right, so let's remind ourselves where we are. And the project for today is to start doing some problems and retraining our intuitions and getting better at um, sort of estimating or getting better intuitive estimations about probabilities, or sort of understanding what happens, how Bayes shows us what happens when we incorporate observations into our beliefs in a hypothesis. So we learned last time that the statement of Bayes' theorem for two mutually exclusive hypotheses is this big messy equation. And I said that you should memorize that. And we've considered it a sort of quasi-English example where I said, look, I look at my phone and I wonder, there's no text there, and my friend hasn't texted me. So I wonder to myself, what's the probability she's mad given that there are no texts? And when that's the hypothesis that she's mad, and the evidence or the observation is that there's an absence of texts, then when you plug in those English terms or those ideas as concepts into this equation for Bayes, we get this equation, this ratio. And we basically have to have four numbers in order to make this estimation. We need to know whether or not, or to assign some value to whether or not she's mad. That's our prior probability, which goes on the top of the numerator on the right. We need to know the likelihood. What's the strength of the connection between the observation and the hypothesis? That is, in this case, when she's mad, how does she react? Does she stop texting? Maybe when she's mad, 90% of the time she stops texting. Okay, that's a very strong likelihood. Or maybe when she's mad, she texts more, so it's never the case that she stops texting, so you put a very low value on that. So you might have a very low likelihood depending on what we're talking about. Very often the likelihood amounts to the reliability or the accuracy of the test we're using. The probability of not H is what's the probability that she's not mad, and that's usually 1 minus the prior. And the probability of seeing the evidence given that the hypothesis is false are a consideration of all the disconfirming cases. What are the other non-mad reasons that she might not text? Maybe her phone's dead, she didn't pay her bill, she's out of service, she's busy, she's not getting my texts, or some other explanation. And what we're going to do is approximate some numbers, or I'm going to give you some real problems where we have numbers for these and we can calculate it out. And we're going to start retraining our intuitions to see how that happens. So here's a problem. Smith just witnessed a hit-and-run accident involving what she thinks is a black truck. And it turns out that black trucks in town are more rare than dark blue ones. The blue ones make up about 80% of the trucks, while black ones make up the remaining 20%. Okay, so it's a weird, maybe it's a company town, or maybe it's a corporate lot or something. Let's just stipulate that 80% of the trucks are blue and 20% of the trucks are black. Smith sees a hit-and-run accident with a black truck. So she's observing one of the minority trucks. Now, furthermore, under these conditions, Smith's eyewitness report is only 75% accurate. That's the likelihood. Let's just stipulate. Eyewitnesses are notoriously unreliable. Let's just stipulate that she's only 75% good at correctly ascertaining the color of trucks in these kinds of cases. That is, Smith gets the answer 75% of the time. So the question is, in this problem, what's the probability that the truck involved in the accident was black, given that Smith says it was black? What's the probability it was black, given that she says it was black? Okay, so now in our equation, here's the Bayes theorem for two mutually exclusive hypotheses. Notice I've used a slash here. That was just an error. I usually use the vertical line, but the slash here means the same thing. Hacking does that in his book, so don't be confused by that difference. And now we can assign some numbers to these. What's the probability of getting that evidence given the hypothesis? That is, the likelihood that the eyewitness would say black, given that it was black, is 75%. That is, you would get that evidence, that is an eyewitness testimony of a black truck, if it was black 75% of the time, because that's how good the eyewitness is at making that designation. The prior probability that it's a black truck is 0.2, given that problem. That's the base rate of black trucks. And if you go back to the example we've considered on the previous slide, there's 20% black trucks. So what's the probability that you get that evidence or that observation, given that it's not a black truck? Well, that would be 1 minus the prior, or 25%. The probability that the eyewitness would say black, given that it's not black. And this is the eyewitness's error rate or the false positive rate. So it's the difference between, here's the true positive rate. The witness gives a true positive rate of 75% and a false positive rate of 25%. And the probability that the hypothesis is false is, that it's a black truck, is 0.8, and that's 1 minus 0.2, or the percentage of black trucks. That's not true, sorry, the blue trucks. There's 80% blue trucks and 20% black trucks. So now when you plug those values into this equation, it's fairly simple. 75 on the numerator, you got 0.75 times 0.2, and then the denominator, you got 0.75 times 0.2 plus 0.25 times 0.8. So that's just plugging in those four values, which is all you need in order to answer or get the result for this Bayes theorem for two mutually exclusive hypotheses. When you crunch the numbers on that, you get a 42, a 0.42. So what is the question that we've just answered? The question we've just answered is, what's the probability it is a black truck, given that the eyewitness said it was a black truck? Okay, so previously we might have thought it was higher. The base rate here of black trucks is just 20%. So there's not many black trucks, but she said it was black and she's somewhat reliable. So her observation has now been folded into the base rate, and it's upgraded our information. So now that we think that there's a probability of 0.42 that it actually was a black truck, given that she said it was. And another way of saying that is to say it probably wasn't black. It's a higher probability than 20%, which is our initial estimation. Suppose I said in town, 80% of the trucks are blue and 20% are black. A truck was involved in an accident. What's your guess on the probability it was a black truck? Now, if that was all the information you had, you'd just say, well, 20%, because 20% of the trucks are black. And then I added this new piece of information. I said, well, furthermore, a 75% reliable witness said it was black. So Bayes' theorem lets us upgrade or improve that, fold that number in, and now we've moved up to 0.42. Still probably not true, but it's better than 20%, which is where we were at the beginning. Okay, so the addition of a 75% reliable eyewitness's testimony to a 20% base rate brings this answer up to 0.42. Okay, so here's another Bayes truck problem. Suppose we run the same hit and run scenario, but the rate of black trucks and dark blue trucks is 50-50. So in the previous case, we had 80-20. Now suppose trucks are 50-50, and we'll keep the eyewitness's reliability the same. So suppose the eyewitness is still 75% accurate in these conditions. So now we'll ask the same question. What's the probability that the truck involved in the accident was black? Previously, when the rate of blue-black trucks was 80-20, the answer came out to be 42. What's going to happen here? Okay, so if I asked you, without the eyewitness testimony, that 50% of trucks in town are blue and 50% are black, and a truck was involved in an accident, and I asked you, okay, so what's the probability it was black? Well, you'd say 50-50, because all the information you have is just to know that there are 50-50 distribution in the population. So now I'm asking, okay, suppose furthermore that a 75% reliable witness said it was black. Now what do you think? Well, Bayes lets us plug in the values. And here's what it comes out to be. So now the eyewitness is still 75% reliable. The base rate of black trucks is 0.5. The eyewitness gets it wrong or has a false positive of 0.25, just like before. So the eyewitness gets a mistake, 1 out of 4 cases. And the probability that it's a blue truck or a not black truck is still 50-50, 1 minus the base rate. So now we've changed those two numbers. We've changed by the distribution of black and blue trucks in the population. When you plug those numbers into the equation, you get this, and when you run the numbers, you get 0.75. Okay, so that is the probability that the truck was black, given that the eyewitness said it was, and a 50-50 blue-black truck distribution is now 75%. That's to say it probably was black. Okay, so what happened? We had a town where blue and black trucks were 50-50 distributed, and one of them was in an accident. What's the odds it was black? Well, 50-50. Okay, furthermore, a 75% reliable witness said it was a black truck. We run it through Bayes, and now we get the answer that it's a 75% probability it was black. That's interesting. So now with a 50-50 distribution, the answer to the problem, the posterior of the Bayes theorem, comes out to be the same as the reliability of the eyewitness. That'll come up again in a second, so just think about that. So we went from 20, previously we went to 42 with the eyewitness making their observation. Now we've changed the base rate and the eyewitness makes their observation. Now we've gone to 75. Okay, so what we just showed then is that when the base rate equals 50-50, the prior is 50-50, then the posterior probability is just going to be equal to the likelihood. That's a useful kind of rule to let us sort of recognize what's going on. What happened? The probability that the truck was black is the same as the eyewitness reliability rating. Why did that happen at the base rate of 50-50 but not at 2080? Well, what would you expect to happen if the base rate was above 50-50 and the distribution was in favor of the eyewitness report? I mean, think of it this way. The eyewitness is 75% reliable, and in the first case, there's only 20% black trucks, and the eyewitness said something that ran against the bias in the population, that the population was running counter to. That is, the eyewitness says a black truck, but black trucks were in the minority. So what happened? The minority of black trucks pulled the eyewitnesses' testimony's reliability down. They pulled the answer down from 75 to 42. But if it's a toss-up, if it's a coin toss over whether it's blue or black trucks, and then we got no reason to prefer blue or black trucks one over the other, and the only reason we have to think it's black is the eyewitness said it was black, and the eyewitness is 75% reliable, then the answer is it's 75% probable that it was black, because you've got no other piece of information that's being incorporated or changing our assessment about the real answer about the posterior. When the base rate is 50%, then there's no bias in the population. The only bias that gets folded in is the likelihood or the eyewitness's reliability in this case. So is it a blue or black truck? It's a toss-up at the outset because it's 50-50. But if it's 75% reliable eyewitness says it's black, so now the posterior is 75%. That's all you've got. It's the only piece of information you have, and it's only 75% good. Okay, so a new problem. Imagine the same problem, but the base rate of black trucks and blue trucks is now 90-10. That is, so we started out with 80-20. Sorry, I've got it reversed now. So imagine now that the vast majority of trucks in town are black trucks instead of the minority of trucks are black. The vast majority of trucks are black trucks. And furthermore, a 75% reliable eyewitness said it's a black truck. So now you've got the bias in the population pushing up, and you've got the eyewitness pushing it up. So now what's the probability that it was a black truck given the eyewitness testimony? Now the bias in the population, that is the 90% black trucks, and the eyewitness reliability will push the posterior answer to Bayes higher. So here it is. There's Bayes' theorem for two mutually exclusive hypotheses, and now the witness's reliability is still 75%. The base rate of black trucks is now 0.9, where we started at 0.2 originally. The error rate, the false positive rate that the eyewitness makes is 0.25. And the probability that the hypothesis is not true, that it's not a black truck, is now only 10% because of the base rate. That's 1 minus the base rate. Or the percentage of blue trucks is now, in this problem, only 10%. So now when you plug those numbers into this equation, you get 0.96. Okay, so that's really interesting. When the base rate is high and an accurate test is positive, then the answer will move more towards certainty. It's a very high likelihood that this was a black truck. Most of the trucks in town are black trucks, and the eyewitness said it was black, so it's a very good, very high probability. So now, what are the lessons here? Actually, you can see all three of them now. So here's the three cases. We looked at 20/80 black blue trucks, 50/50 black blue trucks, and 90/10 black blue trucks. And we kept the eyewitness reliability the same in all three of those cases. And Bayes gave us this answer, 0.42, 0.75, and 0.96. So that is, as the rate of black trucks goes up, the numbers compound, and it moves from 42 all the way up to 96. What's going on here? What does this suggest about how we should revise or retrain our intuitions about base rates of a property and a population and the test we use to measure that property? Well, there's several things that we're starting to see here. One of them is that we shouldn't ignore base rates. Base rates have a big impact on the answer to the equation in Bayes. In the first problem, even the eyewitness testimony wasn't enough to make it believable or make it probable that it was a black truck because there weren't many black trucks in the population. We also learned that if number two, if the base rate is 50/50, then the posterior or the answer to Bayes is just the same as the likelihood. That is to say, the likelihood or the eyewitness testimony or the accuracy of the test is the only piece of information we have because the other information is just a toss-up. It's a 50/50 even match. So only the accuracy of the test matters in that kind of case. And third, the posterior, that is the left-hand side of the equation, is sensitive to the base rate. If the bias in the population favors the test, then the posterior will be high. When the bias in the population is contrary to the test, then the posterior will be lower. That's what we saw at the 0.42 versus the 0.96. And you'll have to look at those problems some more. And then you can imagine the other sorts of examples we're going to consider is what happens when you adjust or change the reliability of the eyewitness. That alters the outcome of this equation too. Okay, so what have we done? We have been considering Bayes' theorem. This is, again, is Bayes' theorem, the general formulation, but we've been looking at Bayes' theorem for two mutually exclusive hypotheses. We've been using this. We just considered blue and black trucks only today. And Bayes is showing us how to incorporate a base rate with an observation where there's percentages attached or probabilities attached to both of those. And then Bayes is letting us either confirm or disconfirm a hypothesis and update our information and update the strength of our belief on the basis of this new observation. And we've learned that if the base rate equals 50, 0.5, then the posterior probability equals the likelihood. That's just the answer. And we've learned that there are these parts to Bayes' theorem. There's the posterior probability, there's the prior probability, there's the accuracy of the test, and there's the likelihood. All right, so we're going to get into more detailed, more difficult problems in part 3. That's all been sort of very safe and hypothetical and very simple, very oversimplified, those kinds of cases. And we're going to start looking at more and more complicated ones and seeing what happens as we fold in observations to our knowledge of base rates at the outset. And that's the end of part